hot species of tin diffuse dried titanium oxide to form a non-equilibrium SN2TiO4. This one
depends on the frequency. So we can see heating properties depend on the frequency. And that is why we believe that the Gelombang microwave heating systems are useful, especially for chemical scientists who like to irradiate some different frequencies to a same object. So in microwave heating systems, captive resonators are usually used for microwave heating. But we think there are some weak points in captive resonators. So one is that seeing the heated sample directly is difficult with using captive resonators. And usually only one frequency input is available. So on the other hand, a new type of microwave heating system, which is called electromagnetic coupling type microwave heating system, was developed in my laboratory. So this system contains the two resonators, which is microstrip resonators on the substrate, and the heated sample between the resonators is arranged, and then the sample is heated by the non-radiative microwave from the these two resonators. And developing 1200 electromagnetic coupling type microwave heating systems is my objective in my master degree. So if this system realized, the sample can be observed while heating, and the frequency band can be easily changed. So I'm going to explain the electromagnetic coupling type microwave heating system. A pair of resonators is arranged here and here, and these resonators are electromagnetically coupled. And this is one of the applications of a non-radiative wireless power transfer that is mainly used for like charging mobile phones or something. And in this heating area, if we put something between the resonators, the sample is heated by the non-radiative microwave. So in this system, we have two problems, with two challenges in this system. So one is that the permittivity dependence on the temperature, and the second one is a power leakage due to the radiated power to the outside of the system. So the resolution was input impedance change is why so if the temperature rises, the permittivity is also changing, and input impedance change while heating. So we put variable matching circuit to the primary port and resolve it. And second, for power leakage, the phase of the secondary resonators is adjusted by changing the transmission line attached to the secondary port. So so if we put two pairs of resonators for two frequencies, we can make a dual band heating system. So today I'm going to explain the 915 MHz and 2.45 GHz combination. So when the input power is frequency of 915 MHz, this resonator and this resonator are electromagnetic coupled, and the sample between the resonators is heated. And also, if the input frequency is 245 GHz, this resonator and this resonator are electromagnetically coupled, and then the sample is heated. So, if fields of two frequency bands are irradiated into the same area, and to make the resonators lengths of both frequencies be in a similar scale, we use lambda over 2 resonators for 915 MHz, which has longer wavelengths, and lambda resonators for 2.5 GHz, which has shorter wavelengths. So we can calculate heating efficiency using a simulation software, which is called CST study suite. So here is the definition of the heating efficiency. Absorbed power by the sample divided by input power, excluding the reflected power at the input port. So in simulation, the heating efficiency was calculated with the condition of the sample was pure water, input power was letting 0.5 watt, and in this time we did only one frequency input simulation. So only one input port was used and the other input port was left open. So the electric features of the pure water is shown here. So the epsilon R and tangent delta are different if the frequency is different. So when the radius of the glass tube, test tube here, is 7.5 millimeters, if we input 915 MHz, the heating efficiency was only 19%. And if the frequency was 2.45 GHz, the heating efficiency was 89%. So, what is the difference from these low efficiency and high efficiency? So, low efficiency in 915 MHz heating is caused by mainly low tangent delta. But not only low tangent, also modes of electromagnetic wave in the sample is related to the heating efficiency. So today's objective of study is improving the efficiency in 915 MHz heating by regarding the sample as a cylindrical dielectric resonator. So as I said, this sample has a shape of cylindrical shape, so it can be regarded as a 915 MHz dielectric resonator. So if this sample is regarded as a resonator, the constructive interference of E fields from the both side of the 915 MHz resonators occurs, and then large amplitude of electric fields is generated inside the sample, and then high efficiency in 915 MHz heating is expected. So this slide shows how we can make a sample as a make a sample resonators. So a cylindrical sample is treated as a cylindrical dielectric resonators, CDR. The resonant frequency of CDR is calculated by the formula here, and we can see TE mode or TM mode. So in my system, TM mode is mainly generated especially TM01 delta mode is mainly generated. So this mode has the E field with this Z direction and H field with rotating H field. So the resonant frequency in TM01 delta mode is calculated by the approximate formula here. So if we set F as 915 MHz, which is the resonant frequency, and D, which is height of the CDR, set to 100 millimeters, and epsilon R equals to 18.23, which is the ER, epsilon R of pure water in 20 degrees. So from this equation, R, which is the radius of the CDR, equals 70 millimeters, is derived. So this is the result of the simulation. Heating efficiency versus radius of the sample. When the input frequency is 915 MHz, the sample functions as dielectric resonators, and the efficiency increases as R increases. When the R equals to 17.5 millimeters, the resonators function as a CDR, and the efficiency becomes 80%. And the efficiency decreases or increases again, and then the sample is large enough to absorb the almost entire power, the efficiency increases again. So we could show that heating efficiency is high when the sample functions as a dielectric resonators. And this is the electromagnetic fields in the sample. So this is E field and this is H field, which shows these electromagnetic fields of TM01 delta mode. And this is the power loss density in the sample. So power loss occurs at locations with strong electric field. So I was talking about the 915 MHz, and this time I'm going to talk about 2.45 GHz input. So efficiencies are mostly higher than 80%, but only this point with R equals 50 millimeters, the efficiency was lower than 80%. And briefly talk why this happens. So this point and at this higher efficiency point, the standing wave of E fields generated in the sample, but only in this point with lower efficiency, standing wave is not generated. So we can say also in 2.45 GHz heating, it is important to generate the standing wave to realize high efficiency. So this is the electromagnetic fields in 2.45 GHz heating when the R equals 17.5 MHz and the sample functions as a cylindrical dielectric resonators. So power loss occurs at a location with strong electric fields, as I mentioned, and we can see like 5 areas, heated areas, and this is because the diameter of this CDR equals 2.4 times lambda g in the sample. So we can count like 2.5 wavelengths in this direction. So this is the brief summary of the study. So at both frequency input, we could confirm high efficiency. So also we can apply to the combination of other frequencies. For example, when we apply to the combination of 2.45 GHz and 5.8 GHz, we could also realize this high efficiency in the two frequency input. So this is the conclusion and the future work.
I think
Thank you so much.
both of them. Not all.